going to talk about section 2.6, day 2, but I think we need to finish up day 1. I'm pretty sure we did not get through this with both classes. So if you did get to this or you understand this, you can fast forward through. But at this point, I want to just finish up this and then we will look at the next section. So if you remember what we were doing in 2.6 day 1 is we were taking functions and moving them around the xy axis. And the way we did it was if we had a specific function, we were not changing the shape of it, we were just changing its location. So in other words, if we had a function that was x squared, it would still look like x squared does, but it would just be moved to a different place on the xy axis. And that was called a rigid transformation. So if x squared normally looks like a parabola, it was going to still look like the same parabola in a different location. And that means that we had to figure out, are we moving it left? Are we moving it right? Are we moving it up? Are we moving it down? Or the last thing we did was actually flip it over the x-axis or the y-axis. So that's what we were talking about with these 3 graphs. But if we look at the final 3 graphs here, this shape that you see here should resonate in your mind with the shape of x cubed. That's what x cubed looks like. However, x cubed usually has a point on it that's 0, 0. And this one has moved over 2 spaces. So I have to figure out how to take x cubed and move it to the right 2 spaces. And that would mean that I took it was still a cube, but before I cubed it, I subtracted the number 2. And that moved it to the left 2 units. And to double check, if I plug in the number 2, when x is 2, for my function here, I should get 0 out. And that's going to happen. So this is the function that matches that picture. This is an x squared function. But usually x squared starts here, and this one is moved to the right 1 and up 1. So I've got to figure out how to take x squared to the right 1 and then up 1, but still have it be a square function. So the right 1 would be adding 1 inside the parentheses, and up 1 would be adding 1 outside the parentheses. And now I'll have x squared moved right 1, up 1. So this is right 1, this is up 1. This has the shape of the square root function. However, it's flipped over because the square root function would go like this, and this one's flipped over. But not only flipped over because this point doesn't match anymore either. It's flipped over and it's moved up 1. So I've got to do both of those things. I've got to flip it on the x-axis, and then I got to move it up 1. So that means that my function that's flipped over, that happens when I put a negative in front of it. That's how I flip it on the x-axis. If I want to flip it on the y-axis, I'd put a negative inside. So that's going to flip it over, but then I also have to move it up 1 unit after I do that so that it doesn't look like this, which would be just flipped over. It's also moved up 1. So that would be the name of that function. So that finishes out the back page of that. So now we're going to move into day 2, which is non-rigid transformations. So that means if I have a square root function, it might not look exactly like the square root of x. It might be a little shallower. It might be a little steeper. it's going to not necessarily move from where it is, but it might get stretched or shrunk when you compare it to the x-axis. So I'm either going to take my square root function and pull it up away from the x-axis more, that's a stretching, or push it down closer to the x-axis, and that's a shrinking. And that has to do with constant multiples. So that's what's going to do that. Stretching and shrinking, constant multiples. So constants multiplied by the function. So if we look at the absolute value of x, we haven't talked about that one recently. That is graphing like a V. It's a piecewise function. And its steepness is a 1-to-1 ratio. So it rises 1 every time it runs 1. It just over here does it in the opposite direction, runs to the left and rises 1. But this 3 in front of the function is going to change the steepness that it does that. It's either going to stretch it away from the x-axis or shrink it toward the x-axis. It's not going to move it. So this 0.00 is going to stay where it is. But now, if I plug the number 1 into the function, it's going to do its thing and not change it. It's going to keep it as 1, but then it's going to triple it. So the output of my function now is up here instead of being where it used to be, which is right here. 1 went in, 1 comes out. So instead of having the shape of absolute value of x there, it's going to be steeper, which is stretched away from the x-axis. So it's like somebody took it and pulled it up. And that is going to end up making my absolute value function look narrower because it got stretched away from the x-axis. And remember, there's symmetry there. So I'm just, I should have probably aimed more for that. That would be a little bit more accurate. If I plug -1, I'd also get 3 out. So same shape, same position where I start, but it's stretched up. So, and you might think, oh, well, then this one's going to shrink it down. And in fact, it does, because now if I plug the number 1 in, I only get 1/3 out. So instead of being up here, I am a lot closer to the x-axis. And if I plug the number 3 in, I'm actually going to get 1 out. So it's going to take me all the way over to x equals 3 before I can get the function value of 1 out of this function. And it's going to do the same thing over here. So I've shrunk this down toward the x-axis, and it's made it wider. So wider and narrower work for absolute value, work for a parabola. They don't work for every graph. So you want to think about, is it moving away from the x-axis? Is the y values getting larger, or are they getting smaller? So if we put it all together now, we're going to have a bunch of different kinds of functions. Here's x squared. So some things have happened to it. It's not just x squared. The -2 inside, we learned before, moves x squared to the right 2 units. The +2 on the outside moves it up 2 units. And now we have this new idea, the 3 is going to do a non-rigid transformation. So it's not just going to slide right and up and look exactly like it used to. This point, which was the vertex, is going to slide right and slide up. So that's a rigid transformation. The vertex just moved over there. But now, when I plug in, I'm going to subtract 2, I'm going to square, I'm going to triple, I'm going to add 2, I'm going to do all the things this function does. But what's not going to be the same is those 3 points on the parabola that I usually use to figure out its width. Because this 3 is going to mess up those y values. And it's actually going to turn out that if I try to go 1 unit to the right, so let's just make a little table to make this clear. I know that when I plugged in the number 2 for x, I got out the number 2 because I plugged 2 in here and this became 0, and I tripled 0 and I added 2 and it was 2. But now if I try to go 1 unit to the right and plug in a 3, 3 minus 2 is 1, and I triple 1 and I add 2, and now I'm all the way up here at 5. So what's happened is, instead of being a parabola that I'm used to, the width of, it's gotten a lot skinnier. It doesn't do what x squared does beyond this point. It is stretched up away from the x-axis. So that one extra little piece of information can help me figure out how narrow to make this parabola. And I can see how it's different than x squared. So with the square root function, that's a little trickier because I only really have the top of the parabola that's flipped over. And so I'm going to realize that this point that's usually at 0, 0 has moved down 4 units. And I'm going to remember from last time that it's flipped on the x-axis when it's down there. And so this point moves down to here, and that's this point on x squared, on the square root of x. But instead of having the shape that I would expect out of x squared, it's flipped over, and it has this kind of a shape. Now, how do I know where exactly to draw it? The easiest thing to do, once again, is to plug in the number 1 for x, and see this is -1 minus 4, and I have like a place to aim for, because that 1-to-1 ratio hasn't been changed. There's no 2 or a half or 3 halves or anything in there that's changing that general idea of how steep this square root of x should be. All it happened is it moved down and it flipped over. So no non-rigid transformation there. Here, I do have a non-rigid transformation. So that 1/2 is going to change something about the steepness. It's either going to shrink it or it's going to stretch it. But I got to know what the cube root of x looks like to even start this thing. And then I can move it up 3. So remember, the cube root of x looks a little bit like the square root of x, but it has the other part to it because the domain is all real numbers. So I want to take that shape. I want to move this point up 3. And then I want to decide, what is this 1/2 really doing? So the idea of the 1/2 is, it should be doing sort of like what the 1/3 does here, which is pulling it closer, pulling things closer down to this x-axis. So it's sort of dampening the curve. And that I could see it pretty clearly if I, again, plug in the number 1. That's always a good option to see what's happening out here. This 1, when it goes in, is going to get dampened to 1/2. And so my y value, instead of being up here at 4, where I'd expect it to be, it's only going to be 3.5. And so I'm going to have a little less steepness to that cube root because of that dampening 1/2. And over here, the same thing is going to happen. There's that symmetry. So I'm just going to draw it. What it would look like if the 1/2 wasn't there, it would be more like this. The 1/2 is pulling things closer to the x-axis, taking it and sort of squishing it in and dampening the height of it. Looking at the next example, number 4, and you can pause this anytime you need to. I think it'd be a good idea to pause it and try to draw some of these on your own and then go back and make sure you did it correctly. It's what I would be doing if I were teaching it in class. This is a flip on the x-axis. This is a stretching away from the x-axis. This is a flip on the y-axis. And this is moving it up 4 units. So a lot going on with my square root function here. So let's do the moving first. It normally would start here, but now it is moved up 4 units. So now that point of origin there is going to move up 4 units. And normally then it would do this, right? Normally it would have a 1-to-1 kind of a width to it and move in that direction. However, this is going to flip that over the x-axis. So it's going to, this negative would make it sort of open down like that. But this negative is going to, I'm sorry, I'm backward. Try that again. This negative is going to flip it over on the x-axis, parallel to the x-axis. This negative is going to flip it over the y-axis. So now we're going to end up with it flipped over here and then flipped over again. And it's going to end up having this kind of a motion to it. So it's flipping this way and it's flipping that way. Or you could flip it this way and then flip it that way. It's 2 flips. That's going to change it to be opening the other direction. And then the only other thing we got to do is deal with the stretch and how that's working. So let's get one more point. We know in general which way it's going. So we'll plug the number -1 into our function. And this will become 1. That's -2. I'm going to add it and get +2. So when I plug -1 in, I'm way down here. And it's taking that function and stretching it and making it more dramatic. Instead of dampening it, it's more dramatic in its movement. The way to figure that out is just to get one more y value that's 1 unit away. I'm using an x value that's 1 unit away to plug it in and get the y value. It just gives me a place to shoot for. And the last one, I know what x cubed looks like. Normally it'll start here and it has these 3 points, 1, 1, -1, -1, and it follows that pattern. So this is going to move that point down 1. This is going to move it left 1. And this 1/2 is going to change the steepness of it. It's going to take it and it's going to dampen it a little bit and pull it closer to the x-axis. So this would be a shrink. But then there's one more thing. It's also going to flip on the x-axis. So if we take it step by step, let's do the moving first. This point is going to move left 1, down 1. So I've moved that with these 2 non-rigid transformations. I'm sorry, rigid transformations of just sliding it. And then the negative means that it's not going to look like this anymore. The negative in front, when it flips over, it means it's going to be this shape instead. So it's going to take this kind of shape. I'm not drawing it yet because I haven't done the stretch, but I know generally which way it's going to go. And now I had to deal with this 1/2. How is that changing the function? So if you look here, I got this point on the curve, which is the point -1, -1. But what about plugging in 0 and seeing how low am I on my y values when I use 0 instead? So -1/2, 0 plus 1. And I want to cube that and subtract 1. So this will be -1/2 minus 1. And that gives me -1.5. So I'm not that much lower when I plug a value of 0 in than I was when I plugged the value of -1 in. So what it's doing is it's making it a little more dramatic now, but it's pulling it toward the x-axis. And then this one, if I want to try another point, I could see what happens with -2. -2 will make this -1 cubed. It'll turn that to +1/2. And I know that then I'm going to be about here. So it's changing the steepness of the curve with that -1/2. It's sort of pulling it closer in instead of being as dramatic as it normally would be. It's dampening it again. All right, on the back page, we can do all of these transformations even if we don't really have a name for our function like x² or x³, and we don't really know the shape of it other than somebody giving us a picture. So here someone gave us a picture of what the f function looks like, just a bunch of different line segments connected. And that means that they've given me combos of x and y. So I could make a table and use all my x values that they gave me and the corresponding y values. And I have a bunch of points, and then if I plotted those points and I just connect them with line segments, that's what the f function is. So then what they're telling me here is that f function can get moved and become a new function that's called g. So if I move that f function up 1, and I move all the points on that function right 2, it will become this new function called g. So the easiest way to move it would be to take all these critical points here that are either endpoints or points where the function changes direction, move all those points where they're supposed to be, and then connect them again. So I can take the point 4, 0, move it up 1, move it right 2. It'll now become the point. So it was 4, 0. I'll move it up 1 and right 2. Now it'll become the point 6, 1. I can take the point 2, -1, move it up 1, move it right 2, and now it's a point 4, 0. So this line segment is the new line segment that used to be here. This is the line segment of f. This is the line segment of g. Now I'll take this point, -1, 2. I'm going to move it up 1 and right 2, and now it's going to be right here. And I can connect that. I'll move this point, -3, 0. I'll move it up 1, right 2. And then I'll move -5, 1, up 1, right 2. And now there is g that looks a lot like f. It just got shifted. The entire thing got shifted. But it's a rigid transformation because it's exactly the same shape, just in a different location. because there was no coefficient. There's no number that I multiplied on. I just slid it up and slid it over. Same idea here. If I want to figure out what H would look like, all I've got to know is what F looks like when I put a half in front of it. So remember that 1/2 is like a dampener, or it shrinks it down closer to the y-axis, x-axis. Because all the points that I had x values for, now the y values are all a half as big as they used to be. So -5 is now matched with a half. -3 is still matched with 0 because a half of 0 is 0. -1 is going to be matched with the number 1, +2 with the number -1/2, and 4 will still be matched with 0. So the effect this has is this point that used to be up there at -5, 1 is now dampened down a little bit. It's moved down a little bit. It's not all the way up here. This point hasn't changed at all, -3, 0. This point, it used to be up at 2 y value, now it's only 1. 2 used to be matched with -1, now it's at -1/2. And 4 hasn't changed. So when I look at the graph of this, it looks like someone just took that and smushed it in. They just dampened it down so that none of the y values were as high or as low as they used to be. And so it's shrunk down toward the x-axis, or dampened, I think, is a better way to think about it. So it's a lot of information. There's a lot of homework that you can work on to get through that information. You may want to watch it again. You may want to think about it again. But the biggest idea here is, how do you know, did you move something or did you stretch or shrink it? Okay, if you moved something, it was because you added or subtracted. If you stretched or shrunk it, it's because you multiplied it. And that's the big difference that you want to be looking for.